Hi guys, welcome to my YouTube channel. Guys, we read the question and then we answer it. So I read, figure shows us a SFG, that is signal flow graph. Using Mason gain formula, determine the gain in forward path. Actually, they are supposed to be gains. And then gains for the loops. Then Roman 3 path determinant. Roman 4 transfer function. So guys, we start off. Guys, I will not take away this paper because we shall be using it. So the first thing guys we are going to look at is what we call gain in forward path. For gain in forward path, guys, we shall look at, we know this is the source node and we have here the sink node. So guys, when we talk of forward path, is that path that moves from this source node to the sink node without traversing any node twice. That means you cannot have a pass moving this way and then here back and then going back again, because guys it will have touched this node twice. And so the forward path always moves forward and does not repeat or move through a node twice. And so looking for those paths, guys, we have this first one, which is G1, G2, G3, G5. And this is what I have written here. G1, G2, G3, G5. That is our first forward path, and it is actually the gains of the forward path. Actually, this is gains. And then from there, guys, we look for another path that can lead us to this point, that is to the sink node. Guys, we can move through this route and then we can move up, or in other words, guys, we are saying that the signal can move through this route, goes up to G4 and then G5. As you can see, we have not repeated any node twice. And so therefore we shall have now our gains, which is G1, G4, G5. From there, guys, if we check, we find that we don't have any other route, any other forward path. And so, guys, we now go to what we are calling the loop gains. For the loop gains, guys, we still use this picture, whereby, guys, we have now to look for the loops. And the loop gain, first of all, we understand the loop is when we move from one node to another and back. Like if you move from X3, you can move G2, H2, and then you go back to the same node. And of course, not transversing any node twice. So the first loop gain is loop 1, which is G2, H2. And because of this negative, guys, we put a negative here. Coming to loop 2, we can have this loop, that is G1, G2, G3, G5, and H1. So we move from this point, we move loud like that, and we come back. That is the signal would move that and come back here. That is another loop. That is G1, G2, G3, G5, and H1. Of course, in the negative, we put it there. So loop number 3, we have this loop, that is G1. We move to G4, to G5, and to H1 once again. So that is also another loop. And apart from that, guys, I don't see any other loop. So from there, guys, we can even now remove this paper, because already, guys, we have been able, but still we have something else, which we call the path determinant. So guys, when we come to the path determinants, it's actually the determinant of the CFG, and it is used to calculate the transfer function using what we call Mason's gain formula. So for the path determinant is represented by the delta, and this one is equal to 1, this is the formula used, 1 minus the summation of all loop gains, all the loop gains, plus summation of non-touching loop gains, and I have left supposed to say non-touching loop gains taken two at a time. So guys, I have not written two at a time, but not that. All the loops, we add them together, minus summation of non-touching loop gains taken 3 at a time. And guys, we can continue taken 4, taken 5 at a time like that. And so for us, guys, as you can see this graph, of course we have the loop gains, as we have already said, and then we come to non-touching loop gains. Guys, we look for any loop that does not touch another, or any loop that is alone and it is apart from others. So as you can see, guys, you can see all the loops are actually interconnected. All these loops are actually interconnected, and so therefore we don't have any non-touching loop. And so therefore, guys, we can have now the delta, that is the path the determinant, the overall determinant, that is path determinant, which now will be given by 1 minus. We now have only these loop gains, and this is what I have written from our loop gains. Now coming to delta k. For delta k is calculated with the kth path removed. That is, we have two paths. We have path 1 and path 2. So we come to path 1. Guys, as we go through the path 1, we remove all this. That means, guys, if we were able to lab, we could lab that path. And then, guys, we are now from there check if there is any loop. So, guys, unfortunately, because we have labbed the path, we shall not have any loop, because all the loops we had passed through that path. And so, therefore, guys, we shall have now delta 1 will be now 1 minus 0, because as we have said, is actually delta, but now calculated with the kth path removed. The same way, guys, if you come and remove path 2, you find it will touch every loop, even this small loop, as you can see, because of this node. When it is removed, this loop will not be able to come back here, because you shall not have a node. And so the same case happens to that. So from there, guys, we just now come to the what we call the Mason gain formula. For the Mason gain formula, you can see it's right here. It's written like that. That is, transfer function equals to 1 all over delta, summation from k equals to 1. These are the number of paths up to the last path, pk, the kth path, and the delta kth path, kth. So guys, for us we only have 2, and so guys, we just now come and fix our figures. We have the P1, which is G1, G2, G3, G5. Delta, guys, we found delta 1 was 1 and delta 2 was still 1. The path 2, this is the path 2 gains. All over 1, according to the equation, all over the delta. And guys, the delta was 1 minus all the loops gain. And this one, because they were negative, the minus here made them to be now positive. And so guys, thank you. For this is now our transfer function. Bye bye.